Electromagnetic compatibility, in short also called EMC, is an essential aspect of modern electronics, and it ensures that devices function properly without causing or being affected by interference from other electronic signals. EMC helps electronics meet regulations and allows them to peacefully coexist in the busy world of electromagnetic fields. The function of EMC essentially is to make sure of three things. 1. Is to ensure electronic devices do not emit unwanted electromagnetic energy. 2. It is to make sure that electronic devices meet certain levels of immunity to external electromagnetic influences. 3. To ensure that the device does not generate interferences within itself. This is essentially where EMC begins. Understanding EMC begins with the fundamental principles of electromagnetism. Electromagnetic fields are generated by electrically charged particles and can affect the behavior of other nearby objects. In the context of electronic devices, these fields can originate from various components such as processors, digital circuits, and power supplies. Electromagnetic compatibility has come a long way since electrical and electronic engineering started. It all began in the late 1800s and early 1900s when radios and electronic devices were taking off. Back in the early 1900s, when radio communications were booming, interference became a big problem. Equipment like spark gap transmitters, commonly used in radios, caused a lot of interference across different electronic devices. This was the start of EMC worries, mainly about radio frequency interference, also called RFI. During World War II, the use of radar and other electronic gear in warfare brought attention to electromagnetic interference issues. This led to the first guidelines for EMC, aiming to reduce interference among military equipment. After the war, as technology boomed, more electronic devices flooded civilian life, making EMC important not just for the military, but also for civilians. Over the years, technology has greatly changed electronic devices. In the 1950s, the bipolar transistor was introduced, followed by integrated circuits in the 1960s and microprocessors in the 1970s. As devices became smaller, the signals they used also became smaller, needing shorter communication times and higher frequencies. Before, electronic devices used vacuum tubes as switches, which were bigger and slower than today's technology. In the late 1970s, digital signal processing became popular, replacing slower analog signal processing with faster digital signals. But this shift also affected the signal spectrum used by devices. With more digital signals, the frequency spectrum became more crowded and harder to manage. Faster digital electronics meant more potential for interference, due to the rich harmonic content of these signals, so EMC became crucial in electronic design. Organizations like the FCC and IEC started setting standards to manage EMI. Other committees such as the CISPR were also formed. CISPR, formed in 1934, which stands for the International Special Committee on Radio Interference, takes this name from its French translation. It is a specialized committee within the International Electrotechnical Commission, or IEC, focused on setting international standards for electromagnetic compatibility and radio frequency interference. In today's world, EMC is very important for all electronic devices. As technology advances, devices become smaller and more densely packed, increasing the risk of electromagnetic interference. Devices need to maintain EMC to function properly and avoid interfering with nearby electronics, as well as within themselves. With the rise of wireless communication and the Internet of Things, or IoT, EMC becomes even more important, as devices need to work together seamlessly in a crowded electromagnetic environment. One thing we need to clarify is the confusion between EMC and EMI. EMC, or electromagnetic compatibility, is a term used in electronics to describe the ability of a device or system to operate without interfering with other nearby devices or being interfered with by them due to electromagnetic radiation. EMI, stands for electromagnetic interference. It refers to the disturbance caused by electromagnetic radiation from an external source that affects the performance of an electronic device or system. EMI can manifest as noise, distortion, or even complete failure in electronic equipment. It can be caused by various sources such as nearby electronic devices, power lines, radio signals, or electromagnetic radiation from natural sources. EMI is the unwanted interference itself, while EMC is the ability of devices to tolerate and function properly in the presence of such interference. To successfully address EMI and ensure EMC, it's essential to understand the roles of source, path, and receptor in the interference equation. Let's break down these components. The source is where the interference originates. Think of it as the originator responsible for creating electromagnetic disturbances. This can be an electronic device, a circuit, or any element within a system that generates electromagnetic noise. For example, a digital processor or a high-frequency component in a device can act as a source of EMI. The path is the route through which the interference travels. It's the medium that carries the electromagnetic disturbances from the source to other parts of the system or nearby devices. The path can be wires, cables, traces on a circuit board, or even the air for wireless signals. The quality of the path can determine how effectively the interference is transmitted. The receptor or victim is the device or system that suffers the adverse effects of the EMI. This can result in malfunctions, disruptions, or compromised performance. For instance, if EMI from a nearby cell phone disrupts the operation of a medical device in a hospital, the medical device is the victim in this scenario. From this, we can see that to tackle the EMC problem, we have essentially three ways. 1. To reduce or eliminate the emissions at the source. 2. To reduce the quality of the path where the interference travels. 3. To make the victim less susceptible for interference. To go a level deeper into the explanation, we can already separate EMC into two approaches: intrasystem EMC and intersystem EMC. Intrasystem EMC is when we are discussing electronic systems which are very close to each other in a very compact system. This means that the chances that their levels of emissions may interfere with one another become higher, and we have to be more cautious. So in this case, the installation process becomes very important, and it can directly affect the EMC behavior of the system. This is where it becomes important to evaluate the effect that each subsystem has on one another. An example of this can be a car, an airplane, or some other system that has different electronic systems very close to each other. Next, there's intersystem EMC, which is likely the one most people know about. It involves ensuring that the whole system operates within specific limits depending on the environment it's working in. This is where we consider the limits based on different environments. For example, industrial, commercial, domestic, and so on. We need to distinguish the two different approaches because we can have some issues if we don't do so. For example, a phone might meet intersystem EMC outside of an aircraft, but when used inside the plane during operation, it might not meet intrasystem EMC because this could cause problems with the aircraft systems. Now, of course, this will depend on the aircraft, but generally, this is why you are not allowed to use electronic devices when on board an aircraft. Let's now see how EMC is divided into categories. We can generally divide EMC into two main branches: electromagnetic interference or emissions, which is then divided into conducted emission and radiated emissions. On the other side, electromagnetic susceptibility, also called immunity, which is divided into conducted susceptibility and radiated susceptibility. Electromagnetic interference deals with controlling the electromagnetic interference emitted by electronic devices. It's important to limit EMI to prevent devices from disturbing nearby equipment. This division involves understanding and managing EMI sources like power lines, radio frequencies, and digital signals. Electromagnetic immunity or susceptibility, on the other hand, is the part of EMC focuses on how well a device can function when exposed to electromagnetic fields, and ensures that electronic devices can still work properly even when facing external electromagnetic interference. This is important as the number of electronic devices around us increases, making the electromagnetic environment more complex and challenging. Why is it so important to address EMC at an early stage of our product design? There are two ways we can handle EMC. One is to design the product and only deal with EMC once it's time for testing, or if tests fail. This is called the SOS approach. The other is to engineer the product with EMC in mind from day one. This is the system level approach. The first approach is more like a betting game. You cross your fingers and hope all is good after the tests. The second method, the system level approach, means considering EMC from the beginning. You assess all the risks, plan, test, and approach the design with EMC in mind at every step. Contrary to popular belief, the first approach is usually the most expensive solution. As the project develops, fewer solutions become available. Extra components are often needed, and costs for engineering, testing, and additional components add up quickly. The second approach is typically the best. It offers less expensive solutions, usually simple and easy to implement. With this approach, the system is divided into modules, and each module is analyzed and possibly tested during development. If EMC issues arise during the development, they are addressed at the module level. Putting off considerations for electromagnetic compatibility until the final stages of product design can lead to significant financial challenges. Here are 7 cost implications of late-stage EMC integration in product design. Let's explore the key cost factors. 1. Redesign and modification costs. Late-stage EMC integration often requires extensive redesign efforts, which can be both costly and time-consuming. Changes like adjusting PCB layouts, relocating components, and adding shielding solutions contribute to increased expenses for materials and labor. 2. Testing and certification delays. Delaying EMC testing can create bottlenecks in the product development process. Initial test failures may lead to multiple testing rounds, driving up costs and delaying product certification. These delays can affect market entry, impacting potential revenue and market position. 3. Production delays and supply chain impact. Late EMC changes can disrupt production schedules, causing problems throughout the supply chain. This can result in higher costs due to rush shipping, penalties, and strained customer relationships. 4. Increased material and component expenses. Efforts to achieve EMC compliance can raise the bill of materials. This includes adding specialized components or materials and potentially more complex manufacturing processes, all of which contribute to higher production costs. 5. Allocation of resources to non-compliant designs. Resources invested in designs that fail EMC compliance represent costs that cannot be recovered. This includes labor, time, and materials spent on non-compliant designs, necessitating additional investment in redesign and testing. 6. Impact on market presence and brand reputation. Delays in product launches caused by EMC non-compliance can negatively affect a company's competitiveness and market share. EMC-related recalls or safety issues can damage consumer trust and the brand's reputation, resulting in long-term financial consequences. 7. Opportunity costs. Resources and time spent addressing EMC issues could have been used for innovation, exploring new markets, or improving the product. This opportunity cost is particularly significant in highly competitive industries where innovation and time to market are critical factors. Early integration of EMC considerations is not just a technical necessity. It is a strategic approach for efficient and cost-effective product design. If you enjoy this type of content, then make sure to join us at the PCB Hackers community. Check the link in description, and I look forward to seeing you there.